Hello, this is a oral report for project number 3, which is modeling celestial mechanics using Verlet integration, or Verlet, if you like to be French. Basically, we get to use our equations of motion, translating our force into an acceleration, basically divide this our force by our mass of the objects. We get to use our convenient units of g to 4 times pi squared, because we're using AU and solar masses and years for time. AU for length, solar masses for units of mass, and years for units of time. Verlet integration is a pretty simple integration where all you need is a starting position, velocity, and acceleration, and from there you don't need any more velocity, as we're assuming that our acceleration does not rely on it, only position. And so from there we can update our position over and over again, and it's fairly accurate. It only has a bit of error, mainly within your time step, and assuming that our velocity does not really depend, our acceleration does not depend on our velocity, and so that would be within there. From there we can look at my code. I've got, so here's my main setup, and we go down, and first I actually calculated using Runge cut of 4, which was not part of the assignment, but it's a slightly more accurate as it does update with the velocity. You can check out my previous project number 4 on that. But afterwards, we create objects for Jupiter with 10 times, 100 times, 1,000 times the mass from our structures. This is all coded within the C programming language. This is the file I use to construct the planet structures and the saving data for the RK4, and also freeing up the arrays they create in memory. From there, we can look at the code over here for the actual calculation. So first, it's just kind of nice having a function to calculate the magnitude, as nothing comes with that in C. Up here we have our math library, our standard IO library. I define my own pi, and this is for my compiler so it doesn't freak out when I'm compiling it. We come in with our Verlet calculation. This also does the animation as well in the Verlet calculation, as it is easier to implement that way, to animate it one bit at a time, similar how it's done in Python. But it is important that this kind of animation, it is important that you have gnuplot, GNU plot, installed on the computer when you're going to run this application. Otherwise, well, it just won't plot, but you'll get data out of it. And so we can look at this, and we start with a bunch of initializations of our constants of the masses, our g constant that we just showed that is 4 times pi squared. Have our time step as what was entered in the main function up here, which will take our number of points and divide it by how many years we run our simulation for. Along with that, we also want to define all of the distance variables. We start that in our initialization, and our acceleration variables from there, we create our first set of R next and our R current. We initialize our next with the initial settings that we showed in the beginning, with our x1 is equal to x0 times v0 delta t times 1/2 acceleration x times the time step squared, in which we have our time step squared, 1/2 acceleration, our initial velocity times our delta t plus our original r's, which we initialized up here. Going over this several times, as now we can start a loop, and at the beginning of the loop we initialize our R current with our R next, so then it'll cycle through each time. And I put this one at the beginning of the loop and R minus equal R current at the end of the loop, because you don't need to update R minus until you've already done your calculations, and R current needs to be there for the first running of the loop for however many times it's going to run, which is based off of our number of iterations. And so it's a very simple loop where you update the distances between each object, you find the acceleration of each object based off of those distances between, and so we divide by the magnitude of the three distances in x, y, and z for the specific from one planet to the next. I'm just calling them generally planets, while it can be any celestial object. It's just easier to refer to each one as planets. There we have, and so one's negative and one's positive in each. You just sort of think of the distance from one to the other and the other to one. And so we go into each one, and just like we explained earlier, 2 times the current minus the previous times your acceleration times our delta t squared, which is much faster just to do delta t times delta t rather than using the power function on that. But I mainly wrote the power function for readability here, and with dt it's not necessary for readability as it's fairly obvious. Next we print all the data to a file with just separated by tabs, /t as in any print function, and then we flush it out so then the file can be completely updated, and then we send that data all to newplot with the command of telling it how to plot and which of parts of the data correspond with each planet. And it's actually going to take the planet's name that we put in there. We can just simply put that down for now to show you how it takes each of the names and puts it in there, so then each will have a proper title. Then we flush the new plate. At the very end, we'll close our data file and our new pipe in the command line, which that's what this is doing, is it opens up new plot within the command line, persists it to keep it around, has our data file so we can open it up and plot it. And we also want to make sure that this loop is really only going to run if new plot opened. Otherwise, we just don't run it at all. So that's our for that integration. And then I have an RK4 implementation as well, although in my code I only am running RK4 for the initial setup, so I don't actually do RK4 with the 10, 100, or 1,000 times in Jupyter. But that's not what the assignment's about, so I only ran it once just to have something extra and fun in there to challenge myself. And then finally we have the constructor for our object within our planet calculations.c file. Therefore, well, I guess it's best just to show a demonstration of it all now. I will just open up my command line and run a for let integration. There we go. So as it's calculating, oh, and it already did all the RK4 integration first. So it's going to calculate first the celestial motion for just Jupiter, and then when it's done, it'll pop up for Jupiter at 10 times mass, Jupiter at 100 times mass, and Jupiter at 1,000 times mass. While this is running, it also can be useful to note that I believe, yes, I did half the time step from what was given in the assignment to improve accuracy, and it also didn't really change the time of calculation due to being programmed in C, and C is just a faster language in general than Python, not always. Something nice about plotting a new plot like this is you can move it around and look at this simulation in 3D as you're running it. So you don't have to worry anything about all that. And it takes just about a minute or so for each one. So yeah, we can watch that. And just for reference, the purple line is the sun, Earth is the green line, and Jupiter is the blue within each of these simulations. As we get into it, there was something wrong with my compiled version on this computer, so I brought over the version from my laptop. And who knows, maybe it's just my processor running this file on my desktop rather than the one on my other computer. We'll see. But this is the last time I'm running it, so I'm turning in whatever I see. For some reason, when I was running it before, it wasn't updating the y-coordinate of the sun. It was just updating the x, and so it was going in a direct path without any curve, but as we can already see, our sun is curving. As we can see in the 10x, it curves a good amount, just a little bit. Oh, I scaled out the Jupiter. It's a lot further than that. I was mainly just zoomed in for the sun and for the Earth as it goes around. But there we go. You can see it's still updating over here. And boom, we get our next one. My phone goes off. Going into our next one. It's already going a lot crazier than it did before. The sun's really curving into Jupiter and is taking a much more dramatic action on it at Jupiter 100 times. And which it says up there. But we're going more in for the very center of the whole operation. I find it pretty entertaining to be able to play with it as it's going. Overall, this is a fairly stable system, but due to Jupiter not returning from where it started, it's going to process and move around a lot before Jupiter ever returns to its start. And you get this cool spirograph looking image with the movement of Earth. And that's just about the end of this simulation before we start on to our next one. There we go. And this one takes a very, very dramatic turn. And very quickly as Earth orbits, the Sun making these very speedy orbits. And the Sun actually makes a full stop before returning in the other direction, going back as Jupiter made a nice loop-de-loop. And then the Earth swaps orbit to go around Jupiter now. And now Earth, instead of just orbiting the Sun, is now orbiting Jupiter. It makes this first orbit take a lot longer, but he comes in, swings around, goes back. Of course, with the 3D plot, I could change it up so these could have initial z velocities, but this is just how we do it here. And the Sun makes another bounce back, is coming up. Earth goes for another flyby of Jupiter. I believe that's the end of our simulation. And so, anyways, just to compare with from the very beginning when I did the RK4 calculation, this was from my RK4 data, and we can go to our first one and compare the Verlet integration with the RK4 data, and they look rather similar. I changed up the colors on there accidentally, but I'd say it turned out rather well for the both of them, and we can get accurate simulations of both either way. But when in doubt, I'd probably choose the RK4 for a wider variety of purposes in doing my calculations, but Verlet was the assignment, so that's what I did here. Thank you very much, and I hope you have a great day.